Now, we need to do the noise renormalization. I am doing only cursorily, I mean if for details you need to look at the paper. So, we have 2h, we have 2h h k omega, okay, and we write as h is Green's function times noise, right. So, Green's function times noise and Green's function times noise, noise is cross and cross multiply and that gives you d. Okay. So, this is the full Green's function. Okay. But look, now h is at a big small wave numbers, so or large scales. So, I can also expand h. Okay. So, the idea is that we expand h. So, the idea, so what we do is we write, so this is standard G. So, we have h is G, then we write. So, look, I look at the nonlinear term now. So, h equal to noise h of k hat is noise k hat. So, apologies. Green's function, no. So, I need to put Green's function in first, because G inverse is in the left. So, that will go to right, G naught of k hat, then we have noise plus nonlinear term lambda h 2h. Okay. So, I expand it. So, I have this Green's function and two non. So, the two leading order we write this as, so this h, one of the h, one h will come from the right. So, let us write the first one, this one, and from the right it comes that. So, this is a standard one, which will be G naught and D, right. Noise will give D, right, noise squared is D. But we go to the next term, which will be this G naught, then this 2h, and from this side also 2h, like that. Got it? Now, every h now we write as a noise times G naught times noise. So, we have this, the noise times this and that. Okay. So, we have 4 Green's function here inside. By the way, these Green's functions will be outside. So, if you look at D, this is the original D. Now, I get a correction from here. So, there how many D's are there? The 4 noise, right. So, 4 noise will give you 2 D squared. This will give you 1 D and this will give you 1 D squared, and there are 4 Green's function, right. There is a Green's function, Green's function. So, I think I have the expression here, which I am just going to show. Okay. So, we have 4 Green's function, these are 4 Green's function, 1, 2, 3, 4. So, this like G naught P here, and G naught Q here, and D here and D here. So, this is D squared and 2 vortex lambda squared. But look, Feynman diagrams is nice, that way I do not need to write it beforehand, I just draw the diagram, then I do the calculation. Okay. And we do the integral. So, this is so you can see there is a correction in this D tilde, new noise, which is D plus D squared and some coefficients. Okay. Now, this calculation can be done, I mean if you are patient then you can do it, no problem. Then this is what we get for after coarse graining. Okay. But then I need to also apply this rescaling, right, that is another part. So, I need to apply rescaling, and the prefactor for the noise was this. This is a rescaling part. So, overall I get that. Okay. So, this factor is coming from, this is the G square, well this, okay, no, so not yet. This part is only for rescaling, but D less I am going to substitute from here. So, this is D less. Huh? So, I will get one part from here and other part from here, and that is that. So, this from rescaling and this part from here, from coarse graining. Got it? Well, the idea is clear, no? So, we need to do both coarse graining and rescaling for KPZ. Now, it turns out for vortex renormalization, the Feynman diagrams look like that. It looks pretty cranky, no? I mean, what is this diagram? This is called vortex diagrams. Vortex correction, actually, vortex correction. In fact, this is in particle physics, this is one of the major things, like coupling constant is vortex. So, I am just going to make one, I will show you how to do which one, this one, okay. So, look at this, we have this vortex and 2h, right, 2h, okay. So, what I will do is I will make one h as a Green's function, and so remember h was, if I put the nonlinear term, Green's function and 2h. So, we rewrite this as only this part, okay, I am writing it here Green's, so this h becomes Green's function and 2h like that, okay. Now, bottom one also I do the same thing, Green's function and 1h and 1h, okay. Now, this h is Green's function and noise, so we really write this. So, this guy, Green's function and noise, Green's function and noise, and this is that, okay. So, these are the two arrows, these are two arrows, this arrow is this arrow is this arrow, and this arrow is coming from the left, okay. This is this arrow, if you like, this arrow, and this is my vortex correction triangle, okay. So, this is that picture. It turns out in normal field theory, solid line is same as Green's function, okay, but I tend to write a wavy thing for Green's function, but they write in fact in this convention solid line is also Green's function, but I would like to contrast it here, okay. Is that clear? I mean, so we can also write down for other two, and it turns out you can do the calculation and these guys give you 0. In fact, you can do the calculation to 0 to first order, it is 0. So, no correction in lambda, okay. It is a difficult calculation, but it can be done. It has been done by these authors, and this is a nice book, Barabasi and Stanley. So, there all the steps are done. In PRL is short paper and steps are skipped, but Barabasi and Stanley has done all the steps, okay. So, it turns out coarse graining has no contribution, only rescaling and contribution for lambda, and so that is the equation. So, there is only rescaling, no, there is no g squared. G squared is the strength of, well, that is the term, right, lambda squared d by nu cube, but there is no g squared coming here. But the g squared is not strength of the coupling, okay, they call it coupling, but the coupling is lambda for me. But in the nonlinear strength of in that viscosity correction, there is a g squared, okay. Now, if you put all these three equations, then I get these three equations, okay. I am just rewriting it here, nu equation, d equation and lambda equation. I did show you how to get them, alright. Now, we know what is g squared. G squared is lambda squared d by nu cube. So, I can write down what is dg by dl. How does this g change with L? So, g is the strength of the nonlinear term in some sense in coarse graining and rescaling, okay. So, remember this was the thing which came in this correction, also it came in a viscosity a noise correction. This is a new correction and this is a noise correction. So, it turns out, well, I will skip the algebra now.